like to start off by introducing Lisa Baize. She's our executive for the Wayne Township Education Foundation. She'd like to say a couple words.
Thank you, Santa. Thanks for being here.
Oh, I'm happy to be here.
We're so happy to have you. How lucky are we? Hi, everybody. I'm Lisa with the Wayne Township Education Foundation. For those of you who aren't aware, we are the nonprofit within the school district that raises money, and when a teacher has a brilliant idea, they say, hey, will you help us pay for it? So we fund things like DNA, fingerprinting, Mr. Crosslin would love that. We fund Osmo robots, tons of books in the district, turning a diesel engine into biofuel. We like to think we're in the business of making a teacher's day because we help give them some tools that bring the curriculum to life in the classroom. Plus, we also recognize them for their superhero efforts. We have a ton of Wayne Township staff members in the audience today. Would you guys please stand up and let us say thank you to you for this amazing work you're doing this year? I know we have quite a few, don't we? Yeah, we have. Just when we thought it was going to get easier with COVID, it got a little harder again. So extra thank you to you for your outstanding efforts this year, helping our students manage and learn and just having good school experiences. So Science Claus is just one of the many community programs we do. I want to thank our sponsors because they made it possible for you to come for free tonight. We have the Indianapolis Airport Authority, the American Chemical Society Indiana section, BMO Harris Bank, Fanning Howey Associates, Epic Insurance, and our platinum sponsors, and they help us all year long, IU Health, Canon 4, Schmidt Associates, JMS, and IUPUI School of Health and Human Sciences. Help me thank them for their great support. We're so glad we're able to host you in person tonight. This is our 5th annual Science Claus is coming to town, and last year we did it more virtually, so it's great to have it in person. With no further ado, I want to welcome our Science Claus cast. We have Mr. Crosslin, our scientist in residence, Mr. Ramsey from Bridgeport Elementary, Mrs. Mason from Chapelwood, Justin Abner from Maplewood, and Ms. Kempers from Wayne Township Preschool. Please join me in welcoming Science Claus is coming to town.
Thank you. So, my name is Rick Crosslin, but this time during the year, I'm better known as Science Claus. And I'm really happy to be able to do this and that you came because something special happened in 1827. One of my science heroes by the name of Michael Faraday started doing a Christmas lecture series, some science shows. And what he did these on had to do with lighting a candle. If I can get mine lit, there we go. And he did 6 different lectures, but what was important about his talks, it wasn't just for the King of England, it wasn't just for the rich people, it wasn't just for scientists. They invited children to come and learn about science. So that's why Michael Faraday is my hero. And they've been doing that at the Royal Institute in London every year since then, except for maybe one year during World War II. And we've been doing science to help celebrate science. Now, he chose a candle. He chose a candle because he thought, and I agree, that you can learn almost all the mysteries of science by studying candle. I love a candle. And I'd like to introduce the rest of my cast. Why do you like a candle, Mary?
Well, my name is Mary Mason, and I'm from Chapelwood Elementary. And my candle is representing the solid. And solids have a definite shape and a definite volume.
Hi, I'm Allison Kempers from the Wayne Township Preschool Curriculum Coach and Educator. And I love candles. It reminds me of the birthday parties. It reminds me of relaxation. But also, I love liquid. And this represents liquid. And liquid takes on a definite volume, and it takes the shape of a container. Yes, science rocks.
Hello, I'm Justin Abner from Maplewood Elementary, and I like candles because it changes a solid into a gas by the heat, and it changes the solid into water vapor and carbon dioxide. And you can see the gases changing by the colors within the flame. Really cool stuff.
What's up, Wayne Township? I'm Keith Ramsey. I'm from Bridgeport. I love candles because they illustrate combustion.
You got a yay on the combustion. So I was thinking about Michael Faraday, and on Earth we have up and down because of gravity, and you have updrafts, the convection currents of making this candle go up. But I wonder what a candle would be like on the space station where there's microgravity. And when you get home, look it up and see the shape of a candle inside microgravity. Now, if Michael Faraday, we should do something special for him, and not a candle. I think we're going to do something that I've never tried before, but let's give it a shot. What if we had, let's see, if we could cook a hot dog, without using a pan. You want to turn that on for me in just a second? And we're going to try to see if we can make this hot dog float in air. I think it's called, is it the Kawanda effect?
Kawanda.
Not Black Panther, Kawanda?
Not Wakanda. Kawanda.
The Kawanda effect. So the Kawanda effect says if I can get this air going here, it should make it, let's see. Whoa, did you see that? Let's try it again. Let's see. Whoa! Let's try it one more time. This is a slippery hot dog. You almost got it cooked for me? One more time, guys. Now we got the hot dog.
No, wait.
What? Mustard.
Mustard. You gotta have mustard on your hot dog. You gotta have. Wait. You gotta have relish.
Relish?
You definitely have to have relish. For sure. Oh man.
No. I'm sorry, but I don't allow ketchup on hot dogs. Are you kidding me? What are you, 2 years old? Who has ketchup on hot dogs? Anybody? Okay, fine. Fine.
Wait, I think, Mr. Aric.
Yes,
I
thank
think
you.
you deserve this.
This is my
This nice hot dog right here.
favorite part of the show. Thank you.
Our first section, Santa's going to help. And what is it? What is our first section tonight?
Our first section is
Air pressure. Air pressure. Thanks, Santa. So, I don't know if you guys have noticed this or not, but we have a can going over here, and this can has some air molecules. Here's my air molecules right here. And these air molecules, when they get hot, they start really bouncing all over the place and bouncing. And the hotter they get, some of them are bouncing out of the top. But if I turn it down to just normal room temperature, the air molecules are kind of slow. And if I add some ice to it on the count of 3, 1, 2, 3, the molecules will freeze. So what we're trying to do here is a little experiment that's going to be kind of interesting. So I think this is about ready to, let's try this one, okay? Let's see. Here we go. I'm going to take this off of the heat, put my gloves on. And this one is going to be interesting. Are you guys ready? Okay. So let me turn the heat off of that. There we go. And we're not going to have an explosion. I hope we have an implosion. Pretty hot. And I'm going to close the lid now. See what happens here. Right now, my molecules are really excited. They're going crazy. And they're all trying to get back in the can, but if I close the can, let's see what happened here. I want to close this really tight. And what's going to happen to our how's the molecules? Slow it down. All right. All right, let's put some ice in here. And let's put this. Are you ready, Mr. Ramsey? All right. There we go. Set it straight like that. Now, you guys keep your eye on this because the more ice we put on. Did you hear something? Whoa! It's starting to get imploded. In fact, if I have an atmosphere bar, Mary, where's our atmosphere bar?
Got it right here for you.
And this atmosphere bar that Mary has, that weighs 14.69 pounds. And that's pushing on every inch of her. So right now, all of the air from here to outer space is trying to crush this can. I think we can make it a little bit faster. Anybody know what's in here? Liquid nitrogen. And the temperature of liquid nitrogen is pretty darn cold. In fact, it's 321 degrees below zero. Watch what happens. Here we go. Wow. Now, I don't know what's going to happen. But those molecules are now really, really... Whoa! Let's do a round of applause for that. And that's the end of our show. Thank you very much. That was pretty cool. Check it out. That was not an explosion. That was an implosion. And I was pretty pleased with that. Good job. Let's round of applause for the implosion. All right. So, my molecule friends back here, we have filled up this balloon. And it has pressure, it has air pressure in it, right? That's just like the press of air. And if I let go of this, everybody say potential energy. And if I let go of it, we're going to have kinetic energy. So everybody, kinetic energy. I'll go first. Let's see what happens. Everybody say kinetic energy on the count of 3. 1, 2, 3. Kinetic energy. It's gone. Oh, there's Peanut. So, as we do this is a big round balloon, and the pressure's pushing in 4 different places. It's pressing on the side, the front, and the back. Let yours go. Let's see which way yours is pushing. Yeah. So, did you see that? So, the ones on the side were equal. Isaac Newton says for every action there's an opposite equal reaction. So the side ones didn't make it go. Mr. Ramsey, let's let yours go and see if yours pushing from the back. Mary, try yours from the back. Really? Really? You know, Michael Faraday and all the people up here, we all... Well, I guess it's like Thomas Edison said, I didn't fail 9,000 times, I just know a bunch that don't work. Let's try 2 more. So, the air pressure here didn't help it. The air pressure out the back didn't help it. The only thing that's pushing it forward is the air pressure pushing in the front of the balloon. Let's try it. 1, 2, 3. That's a good one. Very good. Let's give him a round of applause. Okay. So, we're going to try something here. This is a very, very sophisticated science instrument. I call this a leaf blower. And what's in it? There's a fan that's going to push air. And when it pushes air, like Isaac Newton said, gravity wants the ball to come down, but the air will push it up. Mr. Ramsey, you help me with that big guy right there? Let's see. Ready? I'll start the air. Whoa, that's pretty cool. It's going up. Gravity wants it to go down. Where's my friend? Let's see. Where are my friends at? Here we go. Let's see if you guys. Oh, let's see if they can do it from the back. 3, 2, 1. You have one shot. Throw the ball. Try this against us, okay, ready? Okay. That's Isaac Newton. Ready? Watch this one. Are you ready? That's something different. Check that out. This is where you give me a big round of applause. Come on. Now what you see there was actually what's called the Bernoulli Principle. I made the air go so fast. Well, you explain it.
Well, when you increase wind speed, you decrease pressure in the flow of that wind speed. So when he started to tilt the leaf blower, the ball stayed in place because it was in a low pressure zone. And all the high pressure around the ball pinned it in place.
You know, we could even try that with a bag, a Bernoulli bag. So, Mr. Ramsey, who's my other helper here? I need one more helper here. Let's see, is that you, Mr. Abner? Yes, sir. Okay, get on that end over there. And let's see. I know Mr. Ramsey has a lot of hot air. And I know, somewhere deep down you have a voice hot air, right? All right, back up a little bit. Get close and one breath. Keep your mouth close to it. You need this and why?
Because it's closed.
Okay, fine. Always a perfection. There we go. One breath to see how much you can fill that bag. Just one breath. Close to it. Close to it. Get close. Ready? Go. Wow. How did you do that?
Full of hot air.
There. So now let's try it with the Bernoulli Principle where you keep away from the breath. All right, here we go. So back up, Mr. Ramsey. Let's see what happens here. Back up, Mr. Abner. Now, he's going to stay far back and blow it up, and let's see if we can get more air. 1, 2, 3. That's pretty good. Let's give a round of applause. Nice job on that. But, you know, I like to do one more thing. And What? You don't want me to make messes in here, do you? All right. So if we do this right, if I can make the air go really fast across the top, it should go back up into the air. Let's see if Bernoulli Principle works. Ready? I don't know if this will work. Let's see. Here we go. Sorry, Aric. Sorry. Let's see. Where's my two helpers?
Wait.
What?
I challenge you to a science duel.
I accept your challenge.
Wait a minute, a science duel?
Mr. Crosslin.
Yeah, we're on.
This is Christmas. And you guys want to fight? Okay, fine. What's the rules? Come back to back.
Okay.
Back to back. Okay. Oh, jeez. Miss Kempers, you're perfect. I hate this part. Okay, on the count of 5, you turn around and you toilet paper each other. Okay. All right.
You're done.
Take a big
You're
step.
done.
1, 2, 3. I hate this part. 4. Wait, well, you can't hurt each other. I think you should do something else instead. 5. Go ahead.
Got this!
Oh, no. Let's give him a round of applause. Thank you. So, there is one other thing that we can kind of do with Bernoulli and air pressure. And so you guys can see this better. Let's see. Oh yeah, there's a little bit of theatrical smoke. You guys want to get loaded up? Let's see what we get here. There's one here. There you go. Come closer to me. There we go. Mr. Ramsey. There we go. And so air is all around us. All air is made of matter, and all matter takes up space and has mass. Say that with me. All matter takes up space, has mass. And so this air will be able to see it a little bit better. Let's have a Bernoulli effect smoke ring. Go ahead. In the building. All right, hey, let's give a round of applause for air and pressure. This is a little air pressure device called a hovercraft. And it's homemade. I used it once. And so once. And Santa, I'll meet you next. Mr. Ramsey, be safe. Would you be I don't want Aric to get hurt or my hovercraft. Okay? All right, so when he pushes the button, the air pressure should push down and lift him up. So he's going to have less friction, and we should be able to push him across the stage. All right, let's try it. Go ahead and turn it on. Now this next one is pretty loud. So, Santa, I know that you have a lot of work to do, don't you?
Always. Very busy in the workshop.
And how do you get around the world?
Reindeer.
And what do your reindeer pull?
A sled.
A sled. Well, the best I could do is this sled.
Where do you hook up the reindeer?
Well, you have to use your imagination on this. But this might help. Who's this going to be for? Rudolph. So we've never tried this before, Santa, so let's give it a shot. I think you will need these. We want to protect your ears, and there's your nose, and he's going to sit on this and give it a shot right here. Let me take this part off. And that gas should send you to those guys. So let's see if it works. Here we go. Oh, I hate this part. Okay, you guys, if this doesn't work, I'm going to be able to naughty on it for sure. All right, now you control, there's a lever back there. Everybody, cover your ears. Everybody, cover your ears. Okay. It's going to be blowing. All right, go ahead, Santa. I think I'm still on the nice list.
Our second group is Fire and Ice.
Fire and ice. Now, if you take a look at this, first of all, some of these things, ladies, would you come here for a second? There might be some loud noises. I'm a little late on that loud noise. But before we do that, there are also some of these we don't want you to try at home. And more importantly, and Sand, I'm going to need you on this one. Guys, if you see this, run, okay? Run, I can't help you.
When I think of Christmas, I think of Christmas lights. And a lot of chemical reactions make incredible lights. And I decided to bring some potassium ingots and a little bit of water with me today. When you add elemental potassium to water, it creates potassium hydroxide and it displaces pure hydrogen. But it's such an exothermic reaction that the hydrogen starts on fire. And it starts to burn around the potassium and it makes this beautiful pink glow. Check it out. Elemental potassium in water. Christmas lights. Here's another. You can see the hydrogen building up. Let's try another. There it is. You hear it? You see it? Right on the surface. I had a student last week ask me, Mr. Ramsey, why is it pink like that? Well, when potassium gets really hot, its electrons move to an outer energy level. And when they return to their original orbital, each electron gives off a photon, a particle of light. And those photons have a wavelength of about 620 nanometers. And through the light spectrum, that appears to us as the color pink. Beautiful potassium in water. One more. There it is. Christmas lights brought to you by Science Claus.
Thank you. Now this, we're going back to some ice. This is our liquid nitrogen. Minus 320 degrees below zero. And it's liquefied. Here's some here. It's clear, and you notice, you see the white vapor? You see it? Which way is it going? Up or down? Down, because it's cold. And hey, if you ever get invited to fly in a cold air balloon, don't do it. Which direction does a cold air balloon go? Down. What kind of balloon do you want to ride in? A hot air balloon. And so, let me take my nitrogen. You guys want to help me get your nitrogen? It's pretty cold, pretty cold. But you see how it's clear? And can I have one cup, please? Styrofoam cup? Yep. Thank you. And it's so cold that it looks like it's boiling. What's happening here is, that feels so good. You guys trying it? Miss Kempers, you want to be on this side over here for this group?
Hot air, a lot of hot air.
And so what's happening is my breath is condensing on the cold. And I even have some right here. Now this won't hurt you because if it lands on your skin, it boils instantly. In fact, I can throw this up in the air and it evaporates so quick. Try it again, throw it up in the air. Very, very cold. I guess my best thing to do with this is, remember our molecules at the beginning? Remember all of our molecule friends? Help me with this one, guys. Just get this tray. And let's put it down here on the ground. You got it? And move those things out of there for me. What do you think is going to happen to this balloon? What do you think is going to happen to this balloon when I pour liquid nitrogen on it? It'll pop? So let me put my goggles on. And where are my molecule people? My molecule people at room temperature, what are you doing? What are you doing? What are you doing? I put liquid nitrogen on you and freeze. Let's see what happens. Here we go. Ready? Is it popping? What is it doing? Can I have some more nitrogen, somebody? I think we got them already poured somewhere. What happened to it? Wow, all of the, it's getting smaller. Wow. So all of those molecules have really, really slowed down. Let's see what happens. Here's my molecules. They're frozen, but look what they're starting to do now. They're starting to move again. They're starting to be back to normal. That's a pretty face, don't you think? And it does look like a crunched up blueberry. Some liquid nitrogen. That's the ice part. Keith, what's the next fire part?
Well, another chemical reaction that produces really bright light is one of my favorites, and it involves Christmas gummy bears. In this graduated cylinder, I have some potassium chlorate. Now, what I want to do is start to decompose it into chloric acid. It's a strong oxidizer, and when it becomes a liquid, I'm going to add a Christmas gummy bear. Now, since potassium chlorate is an oxidizer, as it becomes molten, I'll be able to see bubbles of oxygen. That's when I know it's ready to oxidize the gummy bear. Think about what a gummy bear is made of. It's mostly sugar. So if we decompose a gummy bear, it should become elemental carbon. Probably release a little bit of carbon dioxide, maybe some water vapor, and about 20 kJ of energy per molecule of sugar reacting. So watch for that too. I think it's ready. I see molten potassium chlorate. Here comes my gummy bear.
Are you going to hurt the gummy bear?
It's a Christmas gummy bear. Listen to what he says. Oh, I hear him saying, Merry Christmas. You might not hear him because his lips are gummed shut. Look at that bright light. More Christmas lights brought to you by Science Claus.
One thing about I love liquid nitrogen. There were two scientists in like 1810 who found a way to turn nitrogen into a liquid. Now the only problem is this little bit of liquid nitrogen, when it gets warm, it expands 720 times its volume. That's a lot. That's a lot. And when they discovered this way, that opened up a whole new science called cryogenics. So I'm going to put some in here. So are my helpers. We're going to put some in here. That's not a problem. The problem is if I put a lid on it, what's going to happen? It's going to expand and pop. Let's see if I do this right. Oh, I hate this part. Oh, that kind of was good. Let's see. That's a dud. That's a good one. And okay, this Pringles cans, I'm just going to try this one, guys. You don't need to try this one. I'm going to put it in a metal can. And if I put the lid on it, I hate this part. All right. And I'm going to stomp on it and see what happens. Ready? Here we go. Don't put your head over it. 3, 2, 1.5. 1. What do you think?
I think you gotta stomp on it again.
Sometimes it works and sometimes it doesn't. And oh, is it coming out from the bottom? Oh.
Might have a little leak.
If it has a leak, you see it pushing out right there? Yeah. So nature always tries to make things equals. So this one was kind of a dud, but give me a round of applause for trying anyway. Mr. Ramsey.
This next demonstration is one of my favorites. It's the thermal decomposition of butane into carbon dioxide and a little bit of water vapor. And I need my friends to come up here and help me with this. And we're going to get our hands wet. And I need some candles lit over here.
Okay.
So,
I'll light the
All right.
candles away from that.
And I'm just generating a lot of bubbles here that are filled with butane.
No, it's not. It's filled with special fuel,
Christmas gas.
special Christmas
Reindeer
gas.
farts.
That's better.
Okay, let's see what happens when we get that close to the flame. Ah!
Oh, that's pretty good. Let's
Very
give a round of
gassy
applause.
reindeer.
All right. So if you notice, which way does the flame go? The flame goes up. Let's hope so. Otherwise, you're in trouble. And all fires need three things. They need heat, they need a fuel, and they need oxygen. And so when he closes or she closes her hand, she's taking away the oxygen. I would keep it straight up. All right. Miss Kempers, you have a lot of preschool kids out
Okay,
here.
here we go.
Don't get hurt. Good job. That's an A+ for the preschool. And remember, it needs three things: heat, oxygen, and fuel. So if you put all those together, thank you very much for fire and ice.
He's missing some hairs.
I got one more thing we're going to do. This is kind of, I hate this part, but before we do this, I need two of these. Here, Keith and so my wife and daughter in the audience, and so we have a better than that. Come on. Nothing for you, no. Sorry. All right, so what we're going to try to do now is show you how properties change with when something gets really, really cold. So here's some liquid nitrogen, just a little bit. And, here we go. You guys want to, do we have any extra liquid nitrogen? Let's leave that. So one there and bring the other one up, please. Do the whole bunch. You got the whole bunch? All right. Yeah. All right. So they're beautiful flowers right now, and when we change their properties, let's go ahead and, pardon?
They feel nice and soft.
Nice and soft, okay? What are you going to do? You're going to freeze them? Try one.
Let's try it.
At 321 degrees.
You try.
Keep it in there a little bit longer. Put 2 or 3 of them in there. Leave it in there until right now it's freezing more and more. And when you lift it up, watch all of the condensation go down. That's cool. Here, let's do this one, Miss Kempers, over here. Hold it up for a second, and look how all the condensation's going down. But if you squeeze this one, not a good Valentine's Day present. We got the last one. Let's give a round of applause for fire and ice. Ladies, elves, come on out.
The next topic is
Spinning motion.
Spinning motion. Okay, thank you. I hate spinning motion, but let's try it. You guys ready for spinning motion? Yeah. All right. Okay, spinning motion. All right. Miss Mason, you take the lead on this, right?
I don't know. I'm a Boilermaker fan.
Well, they're doing pretty good these days.
Future #1 team. And I grew up with a lot of brothers. And I had to figure out, how can I make things spin? So, you have a plate there. Do you think you can make yours spin?
Well, what I know about science, I'm not a very good plate spinner, but there's a thing in science that if you can make something spin, it's stable. And it's called, Mr. Ramsey, what do we call that?
Angular momentum.
And also gyroscopic stability. Whoops. I was doing pretty good. Mary, how's your basketball going?
You know what? I think I can do that same thing, the stick, with my finger.
All right.
Let's see if it'll work.
as long as this is spinning, I can move it up and down and sideways, but it resists any type of motion like that. And what do you got? What are you doing? Never mind.
But Rick, can you make it go up and catch it?
Up and catch it.
I'm still working on mine.
What I know about science demonstrations, when they work the first time, you should stop.
Yeah, I'll get you. I'll get you.
All right, let's see it. Okay. A for effort. A for effort. All right. Let's see. Santa, I think you should try this one, but I want to stay on the nice list. Mr. Ramsey, you have this one here? We got, let's try, have a seat on our, this is going to be easy, I think, Santa. I'm going to let you do it, but don't throw up. You got the weights?
Right here.
Okay.
So Santa's on a turntable right now, and this turntable with weights will illustrate angular momentum and the conservation of angular momentum. So think of linear momentum, which is just mass times velocity, and that's when an object is linear, when it's traveling in a straight line. It wants to keep going in a straight line. Angular momentum is when something spins, it wants to keep on spinning. So this is mass times velocity times radius. Now, when we think of mass, think of a bunch of kids on a merry-go-round. If you increase the mass, it's hard to slow the merry-go-round down. But if you just got one kid riding, it's much easier to slow down. There's another way that you can affect angular momentum, and that's with the radius. So if Santa holds his arms out and has a radius of a full arm's length, we have to conserve that momentum even when he pulls his arms close to him. And that momentum is conserved by him making more revolutions per minute. So here's his arms. Now when he puts them out, he'll slow down. When he puts them in, he speeds up. Because he's conserving his angular momentum. Way to go, Santa.
I wouldn't mind trying that one more time too, Santa. Let me try it. Let's see here. I get here in the middle, right, Mr. Ramsey?
Well, if you're going to sit on it, we need Justin to help me spin
No.
A little faster. Yeah. I mean, this isn't Santa.
Slow.
This is Science Claus.
All three.
Slow.
I think.
That's fast enough?
Say faster. You want
No.
Science Claus faster. Now, if he wants to slow down, he needs to increase.
All right, ready?
Increase his radius. There you go.
And now
A little faster. There you go.
Whoa!
Conservation of momentum.
Whoa!
Very brave.
Help me. Okay, which way is out? Okay. 1, 2, 3, and there we go. Thank you very much. Okay. Well, we have something very special. Very special. And, yes, this is very special. And we're going to try something. It could be dangerous. Are we ready? Yeah. We don't have music to this, so we might have to have some clapping. Dizzy just thinking about it. There's one. Two. Three. I think she's done this before. We should make it just a little bit more interesting. Are you ready? Here we go.
Guys, need to clap.
Two?
Yeah.
Oh, no. That's crazy. But it is Christmas in science. Okay, so I've been trying to learn something, so maybe I could spin them. Should I try? My family is saying no. I think what you do is you light them and you throw them as hard as you can. As long as I don't drop them, I'm okay. Whoa! So guess what? I'm gonna leave this to the professionals.
Yes.
I'll take it from here.
Okay, there you go. Let's give a round of applause.
Ready?
I don't even know what.
The next topic is sound vibrations.
Sound vibrations. Now, everybody do me a favor. Take your hand right here and go like this and say, sound is vibration. Sound is vibration. Did you feel it vibrate? If you can make something vibrate, it makes sound. And so we have several things here, and we're going to try some things like sound vibration. That is really vibrating. One more time, slowly, or not so loud. Let's see. Wake them up. Now it's vibrating, but what happens if I stop it vibrating? The sound stops. So my friends, join me, would you? We have 3 of these in our pockets. Ready? And if you notice, use your science eyes, and they're different sizes. And so one thing I know is big things make low sounds. Everybody say that. Big things make low sounds. Now I'm a big thing. Now this other part I can't do. I'll try. Ready? Little
Little ones big.
You guys tried that. Every dog in Wayne Township's going, I know big things make low sounds. So I have my big tuning fork, and listen, listen, listen. Can you hear it? Maybe you can hear it better if I amplify it. Ready? You guys try it? Mr. Abner, try your head. Or the bottom of your foot. Or let's try the big one made this sound. Make a prediction with your thumb. The little one is going to make what kind of sound? Let's find out. Ready? Little one, ready? Whoa, little one? High sound. Big one? Low sound. So you can hear sound, and maybe see sound. Hey, can you guys show them a sound wave, Mary?
Ooh, sure.
Let's try a sound wave. Justin, I think I need you for this too. Okay. So, if this represents sound, sound can travel through air, through water, or through a solid. So back up, Justin, one more step. And here comes my sound wave. See if you can see it. Ready? Hello. You see it going through the air? Hello. Now, Mary, you say hello and see what happens. Go ahead.
Hello.
Hello. And Justin, on the count of 3, see if you guys, one, you do yours loud, you do yours soft, and let's see what happens when they come in the hill. Ready? 1, 2, 3.
Hello.
Hello. Can you see the little guy? And the big guy? Try it at the same time. Right? 1, 2, 3.
Hello.
Hello. Which one won? Let me show you. Let me try another thing. Hold on it tight with 2 hands, Mr. Abner. This is a low wave. Mary, you want to show them where the trough is?
Yes.
The trough of a sound wave is where? The very bottom. And the peak, where's the peak? At the top. Now, let me make it a little bit faster. How many sound waves do you see? 3. Do you see the peaks? Mary, come behind and show the peak. Where's the peak at? And where's the trough? And where's the node? What do you think the node is, kids? Yes, middle. Now, this is one speed. I don't know if I can do this. Let's try it. Ready? This is a different, higher speed. How many do you see? I can't do that. You try.
Wavelength.
Yeah, wavelength. There we go. That kind of looks like the cafeteria. Let's give them some sound energy. I need my volunteer, Nathaniel. Nathaniel, would you come up, please? Nathaniel, will you come up, please? Okay, it's my friend Nathaniel. You've grown a lot since I've last seen you on Marion Street. Which one would you like to pick? Which one? Blue, okay. So this is a sound machine. And so it kind of is kind of like this. Ready? You try a tune or something. I like how you do it. Try to hit it flat. You're pretty good. Let's see. Let me try. I'll try a pattern, see if you can follow it, okay? Pretty good. Ready? Okay. Okay, this time you do a pattern. You got me beat. I'll try to follow your pattern. Go ahead. Give me another chance. Come on, try another one. They're getting harder, aren't they? That all you got? That's all you got? Try a good one. Is that it? Let's give a round of applause. Thanks. Yeah, get out of here. Get out of here. Not too much? So you should be able to see the flame. Turn it down a little bit more, please. Blue valve. So if I put this in here, a different song maybe. And so what you're seeing are the different wavelengths. Let's try a different song here. In fact, let's try a megahertz, which this is actually, here we go. I need my daughter up here doing my music. That's pretty cool. You can see the different sound going through. And one of my favorites is we can change this to an actual megahertz. So let's see if we can get that going here. Hold on. So here we have a sound. If I can, let's see, there we go. All right, guys. You know what helps? Putting on my glasses.
So what's happening right now, sound travels through longitudinal waves, and it has to go through a medium so it can propagate through compression. So this whole tube is filled with gas right now, and on the end there's a rubber balloon. So when he holds the speaker up, the balloon vibrates with the sound energy, but that compresses the gas so the vibration actually travels through compression through the tube, and that's what causes the fire to jump up and down. Now, at some frequencies, you can actually see the wave in the flames. That's what he's going for.
You can see the low frequencies.
Yeah, right here. There it is, right there.
And the high frequencies.
That's cool.
How about a round of applause? Take out your palm pipes. Take your palm pipes out. Ready? Okay. All right. Everybody should have one. Here's how you play these. Are you ready? Wait a minute. You have rats on your shoulder. I'm sorry to say, but we've had to cancel the rat trapeze because one of the rats got loose in the auditorium. There's 3 of them. If you guys see anything crawling on your leg or a rat, please raise your hand and we will come and get it. Let's give a round of applause for our Tom Pikes. Okay, Mr. Ramsey.
So I want you to go back in your mind to the World's Fair. This was 1893 in Chicago. It was just 20 years after the Chicago fire, and the city was trying to rebuild itself. The 2 prominent people was Thomas Edison and Nikola Tesla. Now Edison was really arguing for the direct current. He had his light bulb, and if he had his way, all of us would have our light bulbs plugged into a battery. We wouldn't be able to afford to leave the lights on. But Tesla believed that he could create an alternating current that would allow us to reuse electricity. And so he designed a Tesla coil. This was in 1891. And the way that he was inspired was from the induction motor by Faraday. Faraday found that if you wrap copper wire in a circle and you push a magnet through the coil, the solenoid, it induces a volt of electricity. So I brought my Faraday flashlight just to illustrate that so you understand what really inspired Tesla. So here's the copper coil right here. And here's the magnet that drops through the coil. Now if I turn my flashlight on, nothing happens. But if I shake that magnet through the copper coil, it induces just a volt of electricity to make it flash on and off. So this was his induction motor that Faraday created. And this was before Tesla. So Tesla took this idea and he said, okay, I can create that first copper coil, the primary coil at the base. But instead of passing a magnet through the coil, what if I put a coil through the coil? And so he has a secondary coil that he created that allows electricity flow from the spark gap up to this toroid that kind of works like a capacitor. And this happens back and forth hundreds of times per second until this toroid gets charged with positive ions. So many ions that after a while it starts to attract negatively charged electrons in the atmosphere, actually ripping them from molecules and attracting that plasma back to the toroid. When you watch this, it'll look like the plasma is coming from here, but that's not true. It's actually coming from the atmosphere and being drawn to the toroid because it's positively charged. Now, as this happens, it ionizes the air to the extent that it can wirelessly transmit electricity to Edison's light bulb. If you're at the World's Fair, friends, your house is already built. You want the light bulb, but you don't want to rewire your house. And then there's this fellow who said, buy the light bulb and put one of these in your basement, and it'll wirelessly illumine all the lights in your house with no wires. What an amazing idea. The problem was, it's loud, really loud. So as we dim the lights, I want you not just to look at the plasma, but look at this halogen bar. It's not plugged into anything, but it's going to wirelessly turn on. And I have another neon ampule over here. It'll turn on wirelessly as the air becomes ionized and as plasma is emitted in the air. Check it out. This is Nikola Tesla's coil from 1891. In all seriousness, if you have a pacemaker, please step out just while it's on. Is anyone... Okay, just want to make sure.
What about killings in my teeth?
Well, what Rick isn't telling you is he has copper wire around his knee. That's why he's way over there. So stay over there, Rick. All right, here we go. Nikola Tesla's greatest achievement, wireless transmission. Can you see it? Is the halogen on yet? Keep watching. I'm going to turn up the frequency. Now do you see it? Okay. It's going to start getting louder as I turn up the frequency, so don't be afraid. It isn't. It's coming from the atmosphere, ripping electrons from their molecules and attracting them to the toroid. That's what ionizes the air. You might smell that musty scent in the air. It's the same smell that you experience during a thunderstorm because lightning creates ozone. That's the smell of ozone. I'm going to turn it up one more time. One more time. Smell that in the air. You're smelling ozone.
If our computer's still working, I hope it is.
If you ever saw I Dream of Jeannie in the 1970s, had this cool effect when they'd rub the lamp and this big plume of white gas would come out, and behind it, of course, the genie appears. This is an easy reaction to remake with just hydrogen peroxide, H2O2. When this decomposes, it releases pure oxygen, which is this big white plume of gas, so it's safe to breathe. And I'm just going to catalyze it with these pellets of manganese dioxide. You can also use potassium permanganate or even silver will start this reaction. But check it out. Pure oxygen from hydrogen peroxide. This is an exothermic reaction, so I'm kind of holding it up here at the top. If I put my hand down here, it's hot. So I'm just going to put this down here and just imagine the genie appearing from behind the plume. But another reaction that I love, a lot of people call this elephant toothpaste, and again, it uses hydrogen peroxide, and it creates this beautiful foam effect. So in order to do this, I'm just going to fill up this bowl with some hydrogen peroxide and some food coloring, because we want our elephant toothpaste to be colored. Lots of food coloring. And I have to prepare a catalyst for this to start the reaction. So instead of manganese dioxide, I'm going to use potassium iodide because it dissolves very quickly in water. So this just has a little bit of water in the graduated cylinder. And what I'm going to do is just shake this up so it dissolves in the solution. And then the last thing we want to do for elephant toothpaste is just add a little bit of detergent. And Dawn dish detergent does great with this. So I'm just going to put a little detergent in here. Put all of it in? The foam would be over there. So then I'm just going to stir it really quickly. Kind of work that soap into the hydrogen peroxide. Okay, and then I'm going to move some of these things because that foam could fill up the whole tray. And we just want to drag this tray off stage. Okay, so here's my catalyst. I'm going to check it to see if that potassium iodide is completely dissolved. Looks good. And as I add it, again, it's going to decompose that hydrogen peroxide into pure oxygen, but now it's going to be trapped in the dish detergent, in the bubbles, and that's what creates all the foam. It's still exothermic. If you watch carefully, you can see steam coming off of it. Look at all that steam. Elephant toothpaste, brought to you by Science Claus.
Okay, we're going to try the whoosh bottles right now. Now the whoosh bottle is still growing. And now that we have all the vapors in, this is called the whoosh bottle. We'll see how it works. We should hear a nice whoosh sound. And we might have to light this a second time. Let's see, are you ready, Mary?
I'm ready.
All right. I think we want the lights down for this one. It might be a little bit better. We do the lights. Let's see. I think, Mr. Aric, you want another hot dog?
We want another hot dog.
Okay. So we'll do the lights down, and I'll try mine first. And we should see a nice blue flame, and we should hear a nice whoosh. Are you ready? Here we go. Here comes the first one. And it's the vapor, not the liquid. Anything? Anything? Whoa! Pretty good, Mary. Hold on, wait a second, Mary. And the byproduct of combustion, the byproduct is water. When you see a jet airplane going through the sky, it's burning fuel, and you're seeing the white vapor trail from combustion. Mary? So I'm going to put some liquid nitrogen in this. Not a problem as long as we don't do what?
Put the lid on.
All right, so here you go. Here's yours. Got a lid. And Keith, you're going to do one, right?
Yeah.
You have gloves? Okay. Don't do it yet. Let's see. You got a lid. You have gloves. A little more. Okay. And I have some. Now what we're going to do is we're going to drop it. Where's my assistant? You guys ready with the ping pong balls and the Christmas squishies? I want to thank everybody for coming out tonight. We've had a lot of fun doing this. And everybody got a lid for these? Okay. This is going to be a big boom, and I don't know when. So cover your ears. It should shoot things out into the audience. Squishies. And afterwards, you may keep things, but watch the cords and keep your mask on. And I want to wish everybody a Merry Christmas. Here we go. From Science. Are you ready? Here we are. Not yet. Not yet. Ready? Now. Mr. Ramsey, thanks for following directions. And our last one. Thank you very much. Thank you for coming.